All clear?
Question?
Yes.
Have you looked in different Unix operating system about the behavior on zero allocation?
Yes. We have looked at all of those we have looked are also exposed. So none of the Unix we have looked at are not exposed. Whenever you do malloc 0, except in the Solaris kernel, when you do a malloc allocation 0, it does return null, which can be pretty bad, basically, because you need to make sure every call checks for the null return value, which is not always done. This is another issue. Everything we have tested is exposed. This is not Windows specific. We have tested username on pretty much everything. And the kernel or other operating systems, such as Mac OS X on Office. Like, well, basically everything is exposed. Like I had a little table with like exposed things, but I just put it as a bonus slide that you can see offline. But like, basically everything is exposed. It's not Windows specific. Everything has the same POSIX compliant behavior. Now automated analysis. So I'm going to briefly present the tool we have done. And before presenting the tool, I'm going to present 3 different techniques of analysis. So first, I'm going to talk about very briefly about data flow analysis, then about model checking, then about theorem proving. So I'm going to be very clear with very dumb example of what those things are doing. The goal is not to like overflow you with like theoretical masturbation or anything. If you don't understand, just please let me know, because like I don't want to. I want to do the presentation for everyone. So why do we need automated analysis? I mean, sometimes we can just say, okay, we do code review. That's very easy. You just work on malloc and then you check if the size can be 0. But like it's a little more complex than this. Obviously, you can have malloc at like depth 20. You know, you can have like a call stack of 20 functions. And the time you're going to need to check if the size can be 0 can be really long. Like it can take a full day basically for just one site of allocation. So we've done a tool that analyzes all allocation files for us, and that tells us if the size can be 0. So in that case, we get into warning. So this tool can filter 99% of allocation files. So basically, in 99% of the case, we are able to prove that the size is different than 0. So we know that we don't have any 0 allocation problems. However, in 1% of the cases, we're not able to prove that the size is 0. So in that case, we have to warning. And in those warnings that are left, we just check out if there is a security problem. And in those 1% that are left, we found out that around 10% are these security problems. So say if we have 100 warning on 1 million line of code, which is more or less our numbers, we analyze 1 million line of code, we have around 100 warnings, and around that we have around 10% of those that are real vulnerabilities. So we tested that on a couple of Windows components. I'm not sure if the numbers are accurate universally, but from our experience, the numbers are like that. So first, data flow analysis. Data flow analysis is a rather easy and quick technique to implement. Like most compilers use data flow analysis for things like register allocations. So many of you are probably familiar with liveness analysis, like reachability analysis and things like that, even like static single assignment form, which is intermediate form for compilers. So it's an intermediate form specific to data flow analysis and symbolic data flow analysis. So basically, the idea is you analyze what are the dependencies between variables, and then you can like decide, which register you're going to put the data and stuff like that. Obviously, you can do much more complicated analysis on top of data flow analysis, but compilers use them mostly for register allocation and other optimizations, such as like like a propagation of values and stuff like that, like constant propagation, copy propagation, etc. So what's good about data flow analysis is that it's fast, it's scalable. You can do that, and like you can compile the Linux kernel or the Windows kernel. So it proves that it's fast. I should say is that it's a hard-coded algorithm. So you have to write a specific algorithm to do data flow analysis on code. You cannot use a framework to do that for you, or maybe there are frameworks but they are specific to data flow analysis. So when you start with automated analysis, usually you do data flow analysis because it's like the easy way to go. Like you have like a well-documented algorithm. You can, like, for example, like take any compiler book, the Dragon book, or like the modern compiler implementation book of Apple or anything like that. And like everything is very well documented, even online, like like Scholar or whatever. And you can actually find quite a lot of bugs with just the flow analysis. You can find like double free, use after free, and things like that. You can find all of those things without a very complex analysis. You just need to follow the data flow graph. For example, this actually you can see very well, but here you have like each node is a variable, and arrows between nodes are dependency between variables. So here, like in that particular example, the green are malloc and the red are free. The blue are intermediate nodes, like intermediate variable nodes or register you use. And those are memory cells, but what the most important is to know that you can build a graph that is the dependency between variables of a program. So when you do that, you can just do like a very simple like depth first search or whatever graph search, and you just follow and you see, for example, if a malloc doesn't reach a free. In that case, you have found a path where you can have a memory leak, for example. Also, in that path, you can have a free that is done on a non-malloc value, so you can have a free of uninitialized data or like things like that, you know, so malloc free bugs, you know, double